is that all right? Well, good evening, everyone. Thank you for coming, and very nice to welcome back Megan Ancliffe, who was a student here, amongst other things, and then is an architect and a passive house designer, certified passive house designer. So Megan's been an architect. She's been she was lead architect for one of the stations on the Elizabeth line, and now is kind of following, I think, in a way, your interests or your passions maybe for low energy design, working with a new venture and a new group of people called Delta Q. And so we're going to hear about the kind of passive house, I think, principles, but maybe just how it's applied and the kind of issues and problems and complexities, I guess, of that. But thanks so much. It's always nice to welcome back a former student. So thanks. Nice to see you again. Thank you.
Thanks, Will. Is the microphone working? Can everyone hear me?
Yes.
Brilliant. Yeah, so thanks for inviting me to talk about Passive House. It definitely is my passion. So I'll just give a little bit of background to Delta Q, the company I work for, and myself, but then we'll get into what is Passive House and why would you want to build to this standard. I'll go through some of the key design principles, and then I will delve down a little bit into some of the design details that are needed. So first, a bit about Delta Q. We're a passive house and a low energy building consultancy, and we were established in 2010 by our director, Piers Sadler. Do a range of projects: schools, social and private housing, multi-residential, down to single dwellings, and we do new build and retrofit work. And we also work on non-passive house projects where the project is targeting an improved building performance. So things like LETI standards, the new net zero carbon building standard. We also do Passive House training courses, and we've done a number of master classes with the Passive House Trust. That's the organization that promotes Passive House in the UK. And Will already gave me a little intro, but this is just a bit about me. So yes, I'm an architect and a certified Passive House designer, and I studied at Westminster. I worked in transport for a good 10 years in the King's Cross upgrade, but most of my time was on the Elizabeth line, which just won the Stirling Prize. Woolwich Station is the best station. That was the one I worked on. By way of that, I did a bit of community self-building, and then I really wanted a deeper understanding of sustainable architecture, kind of get into the nitty-gritty of the physics and the modeling side of things. So I did a master's in environmental engineering, and at that point, I moved over to Passive House. My experience in Passive House has been involved with larger high-rise, multi-residential housing and student accommodation projects. So diving right in, what is Passive House? So it's a building standard, and it was developed in Germany in 1991 by Wolfgang Feist. He's a physicist. He's shown here with his family, and he's standing in front of the first passive house ever built in Germany. And the technical definition is up at the top there. So a passive house is a building that has reduced its heating load to less than 10 watts per meter squared. That's a really key number, because that's the point. You can deliver all the heating to the building only by supply air. Why that is important is at that point, you can do away in theory with your traditional wet radiator system. So you don't need your radiators, you don't need underfloor heating. So you do need to put a ventilation system in the building, but you're going to offset the cost of that by getting rid of all those old heating systems, and you're going to use the ventilation system to heat the building. Now, to be able to only use air to heat a building, you have to have a really low heating demand, and therefore you need a very efficient building fabric. And that's the theoretical basis of the Passive House standard. It's an operational energy standard, so it's concerned with energy over the lifetime of the building, and it's importantly, oh look, I just got louder doing that. And importantly, it's a comfort standard as well. So it's about very high quality buildings in terms of thermal comfort, indoor air quality, and even noise limitations, and they're all stricter than the standards you get, say, in the UK building regulations. So this diagram shows the 5 key principles that every passive house has. It's known as a fabric-first standard because it really prioritizes insulation and air tightness, but it also requires mechanical ventilation systems. It's a performance standard, so it's not prescriptive. Any form or construction can, in theory, be a passive house, but certain types of designs are going to make it a lot harder and potentially too costly. Any type of building can be a passive house. So I'm going to focus on housing in this talk, but it's been used for offices, retail, educational, healthcare. And I am told there is even a zoo in Germany with a hippopotamus enclosure that's been certified as Passive House, which is very exciting. It works in any climate, so different climates are going to have a different fabric response, but the principles like work in reverse. For a hot climate, there would be keeping the cool in and the heat out. And I think in some respects, this is sometimes why people struggle a little bit getting to grips with how to design and build a passive house, because it's not a simple checklist of U-values you have to meet. It's not like a BREEAM checklist. You have to consider the energy implications of a design from the very start, and you have to embed those in the design. It's actually not revolutionary at all. You can use standard materials, you don't need any special construction processes. It uses building physics to accurately model the energy of a building, and then you have a robust quality assurance process to make sure you build what you designed. That's pretty much what we should be doing as standard. So these are headline passive house criteria. Now, for new build, you've got 3 options. All new builds will have to meet the criteria at the top for space heating, cooling, and air tightness, but we've got 3 different options for primary energy. Primary energy is the total amount of energy a building uses. So they are different depending on how many renewables you're able to get in your building. A classic certification doesn't need any renewables. If you want to go for the top premium, you're going to need to be generating more energy than your building uses. And we have a NFIT version. This is for retrofit projects. It's a bit more relaxed criteria, recognizing it's going to be harder to do in an existing building. And when you compare this criteria, say, to the UK building regulations, the space heating is approximately 75% less, and the air tightness is about 10 times more airtight than a standard building regs compliant building. And just to note, we've got our heating load limit, that 10 watts per meter squared I mentioned. This heating load is actually very unique because it's recognizing we're not just looking at the amount of energy demand over a year, but we're looking at the amount of energy used at any one time. This is really important as we move to net zero because we need to ensure we don't overload the electricity grid as all buildings move to electric. Passive House also has its own modeling software. It's called PHPP. It's an open source Excel spreadsheet, although it's a very complex and detailed one. And the fact that it's Excel is actually one of a real positive about it because it makes it very accessible. If you're working in it, you're getting some results you're not very sure of, you can actually track through the formulas and, if you want to, really understand what's being calculated and what may be working and not working. And it's very affordable. It's only about £200, which is much more affordable than any other kind of modeling software on the market. It's also got a 3D modeling plugin. It's called Design PH. It requires SketchUp. So what we can do is we can take Revit models from the architects, we import it into SketchUp, and then we use Design PH to model our thermal envelope, our geometry, and our shading, and then we can import it into our PHPP file. So on the image here on the right, this is some output from PHPP. This is showing the heating balance in a building, and it's showing it's always a balance between the heat losses and the heat gains. And whatever you've got left over is the red, that is your heating demand. So that's what we've got to keep below 15 kilowatt hours per meter squared per year to be a passive house. So I just want to say about, well, why would you choose to do passive house over any other building standard? And the first thing to say is there's a lot going on in this space, the sustainable building standard space in the UK. The building regulations in the UK are really far behind where they need to be if we're going to do net zero. The government had a plan for all new homes to be net zero as far back as 2016, and it was scrapped. So pretty much since then, the industry's been waiting to see what's going to happen. And in that time, that space has kind of been filled by lots of councils, lots of optional standards, other guidance coming out. Kind of everyone's trying to fill this gap and creating their own sustainable policies, which is really admirable, but it does lead to complexity and quite a lot of overlapping as everyone does it slightly different. We've had the consultation, if you're aware, the Future Home Standard is what's going to replace Part L. It's consulted and we're waiting for it to come out, but it wasn't very encouraging. The fabric standards were not very inspiring, but some exciting stuff happening in Scotland where they're actually consulting right now on whether to make a passive house equivalent part of the building regulations. So the question is, why out of all of that would you choose to do passive house? And I'm going to just go through a few points of why we think so at Delta Q. First of all, Passivhaus is a tried and tested standard. As a concept, it's over 30 years old, which in terms of sustainability standards is quite old. Most of them are much more recent than that. So even though we only built the first Passivhaus in the UK in 2009, we have years of data from Europe. We know that this standard works in practice. This document on the screen here, it was prepared by the Passivhaus Trust, and they've collated a whole load of research papers and carried out their own research on Passivhaus buildings and their benefits. And they've kind of distilled them down to these 6 categories. So I'm going to go through those benefits, but if you're interested in seeing the actual research and the hard facts behind them, they're available on the Passivhaus Trust website. So first and foremost, as it's known for, it's a building performance standard. Obviously, it's got very low energy and it leads to very comfortable buildings. But the most important part of that is how Passivhaus buildings are designed, is how they're built. It hones in on this performance gap. If you've heard of this is the gap between a design energy model and then when you actually build it, how much energy the building uses. So new build homes in the UK have been found to use about 40 to 60% more space heating than they were modeled at design stage. So that's a real problem. And the first graph is a demonstration of that. So this is a typical building regs building. On the left is the Part L building regs energy model. And on the right is how much energy the building actually used in praxis. And on the right, this graph is a series of co-heating tests. So each pair of bars is one building. The blue is the design model. The red is the actual building as built. So what you can see, there were 3 Passivhaus dwellings in this study. Not only are all the bars lower than all the rest, but the gap between the blue and the red is so much tighter. It's really closed down that performance gap. And the way Passivhaus does that, firstly, it has an independent certifier. So this is someone, not the Passivhaus consultant, independent to me, who comes in and does in-depth checking. So all of my modeling is checked. I have to justify all the assumptions, have evidence and calculations for everything I put in the energy model. And then when we get on site, we have to have a lot of extensive photo evidence, all the thermal elements that are installed, that we have the correct products, and we have to verify all of the workmanship. And the certifier checks all of that, and they're the person at the end who says whether you've got a Passivhaus certified building. So the building regs are just starting to move into the space. They're asking for a bit more photographic evidence, but it's just nowhere near the level of checking that you get in a Passivhaus. So the next benefit of Passivhaus, obviously we're in a climate emergency. Lower energy use is going to mean lower carbon emissions. And studies have shown that we need to have very efficient fabric if we're going to reduce peak loads in our buildings. I mentioned that about keeping the loads on the grid low, because as we decarbonize the grid, and if to get all our buildings off gas, if today we moved all buildings to electric, there's not enough power in the grid to power them all. So we need to reduce our energy, our fabric efficiency. We need more efficient fabric so that we have less energy demand when all buildings go electric. This example on the screen here, this is Erne Campus in Northern Ireland. It's a Passivhaus Premium, so it's the very top standard you can get for Passivhaus, and it generates 4 times as much energy as it uses. The other half of this is actually sometimes a criticism that comes of Passivhaus. It's like, well, you're focusing on operational carbon. What about the embodied energy? What about the carbon generated in the materials and the construction processes? And this historically has not been a focus of Passivhaus. And in fact, to make a Passivhaus, you're probably going to use a bit more materials. You're going to have a bit more insulation. You're going to have better windows. You're going to have that ventilation system. So you could argue, well, we've got less operational energy, but we've put more embodied carbon in the building. So the first thing to say about that is when we reduce our space heating to a very small amount, we need much smaller MEP kit. We need a very small heat pump. Potentially, we're not going to have any radiators in our building. Passivhouses, because of how they're built, are much better quality. They've shown to have less replacement and maintenance cycles. And a really key one, it's never going to need a future retrofit. There's a lot of new builds going on now. They're going to need a retrofit in the next maybe 20, 30 years if we're going to meet our net zero targets. But the really important one, I think, is Passivhaus, as I said, is not a prescriptive standard. So you can use any materials you want. So the key point is it's fully compatible with any other embodied carbon strategies you're going to have out there. And in fact, there's now embodied carbon plugins for PHPP. So we really see it as a baseline for wider net zero strategies, including whole life carbon. And this is a lovely example. It's by Archetype, and it's an office. It's Passivhaus certified and using low embodied carbon materials. So the next one, the benefit of health and well-being. When in a passive house, if you've ever been in one, you get this really even, stable indoor temperatures in summer and in winter. It's just got this really high level of comfort. So there's no cold surfaces, there's no drafts, there's no risk of mold and condensation. It's got an excellent indoor air quality because of our ventilation and we're filtering the air. And there's obvious benefits to that in health and well-being. You see it there used for things like here, this is another archetype example. This is a care home. And as well as avoiding health issues with cold homes, it also addresses overheating, which can be just as dangerous to vulnerable occupants. There is an overheating check in the building regs, but again, we have to do a much more robust check in passive house. We've seen often we'll inherit a project, it's already got a Part O overheating assessment, and we realize it's full of unrealistic assumptions that we have to challenge, and we just find what is acceptable for building regs is just not going to be good enough in a passive house. And those same properties of excellent indoor air quality and comfort have also been found to have a positive impact on performance. You really can't understate the importance of good ventilation. There's known links between CO2 levels and impaired cognition. So you see passive house being used more and more for schools and universities. This is an example Delta Q were involved with in Wales. And they have evidence of improved learning outcomes when passive house is used for these types of buildings. We've also found passive house, because it's so airtight and so insulated, it's quieter inside. And this also has benefits for performance. And in offices, they've found reduced absenteeism, improved productivity. And those same benefits kind of have a wider social benefit when you use passive house. As we know, poor housing is known to affect physical and mental health. And low energy means low bills, up to 90% lower bills in a passive house. And so we're seeing lots of councils build passive house for social housing. And this is another excellent example, Goldsmith Street. It won the Sterling Prize in 2019. And the last one that was flagged is financial. Now this is interesting because usually this is seen as one of the drawbacks of passive house, that it's going to be more expensive to build it. But the research has shown if you look at the whole life costs of a passive house, it comes out cheaper than a standard building because you've got your lower energy bills, you've got less replacement and maintenance. So we do find it easier to sell passive house to clients who build and operate their buildings, like local authorities, schools, owner-occupiers. And we do find the upfront costs are going to be higher when a contractor hasn't built a passive house before. They are going to price in risk. The example on the screen, it's not very exciting architecture. Why this one is interesting is this is a builder in Ireland. They'd done a few passive houses before, and they challenged themselves whether they could build a passive house for the same amount of money as a standard building regs building in Ireland. And the answer is they did it. They built this. They quoted it was €130 more to do this passive house. So the point is the industry can do cost-effective passive house. It's going to have to get more experience and do things at scale. Okay, so I'm just going to move into now some of the high-level design principles we use when we're building passive house. Passive house has probably historically been known more in timber frame building, but as it's moved into the mainstream, we're seeing more masonry and concrete frame projects. And building passive house and this type of construction, say for blocks of flats, is still pretty new in the UK. This is the first one that was done. This is Agar Grove in Camden. It was finished in 2018. So I'm going to focus on multi-residential housing and concrete and masonry construction when I'm talking through these details. So just go back to those main principles in a bit more detail. So we've got our thermal insulation. It needs to be a continuous wrap around the building. And the key is it has to install gap-free. And the reason is we're at risk of thermal bypass otherwise. So this is when heat bypasses where you want it to go, which is through the insulation. And as soon as you have small gaps, it's going to leak out those gaps faster. And those gaps, as soon as we're over 3 millimeters, we're starting to get into the realm where we could see an impact on the thermal insulation. And research has shown you can have up to a 19% reduction in the performance of a U value if you have, due to thermal bypass, if installed badly. So if I design my new variant 0.15, my as-built could be as high as 0.18. This is where the performance gap is coming from. Our second principle is we have to have high-performance glazing. So in a passive house, all the internal surfaces can't drop below 17 degrees. And the reason is any lower than that relative to the air temperatures, and the cold surfaces are starting to impact on thermal comfort, and the windows are the highest risk of dropping below that temperature. So you've probably all been in a room where the thermostat says 20 degrees, but you still feel cold. And that's because you're getting drafts, you're getting convection currents, you're getting cold surfaces. You don't get any of those in a passive house. Now in the UK climate, to achieve that surface temperature, we're going to need to do triple glazed windows. We've got, next one is our ventilation strategy. So we have to have mechanical ventilation with heat recovery in a passive house. We need ventilation in all our buildings. We need fresh air, we need to control humidity and get rid of all the water vapor we create when we're cooking and washing and breathing. Now the building regs allows you to do this just with trickle vents and opening a window. But that means when you ventilate in winter, you lose all your heat as well. So the point of using an MVHR system is when you ventilate, you recover the heat at the same time. So you can see the diagram there on the left. We're getting the stale air, which is in red, from our wet rooms, our kitchens and our bathrooms. And before we exhaust it to the external air, it's passing through a heat exchanger. The fresh cold air is coming in and they're crossing over, and it's reclaiming all the heat before it then pumps that warmed air back into the building. And we've got units that can do up to claim 95% of the heat. So you're ventilating your building and you're not losing any of the heat effectively. And people do worry, oh, wait a minute, I'm going to have a ventilation system running all the time, and they're going to use more energy. It uses only a small amount of energy and a lot less than if you're going to ventilate with a trickle vent, and you're going to have to compensate that with your space heating. When we design these systems, they have to be near silent because we can't have people hearing the ventilation because they'll get annoyed and they'll switch it off, and then we really will have a problem. And we have to have high-spec filters. So this on the right is a MVHR filter being swapped out. They need to be swapped out every 6 months. We're living in London. That's what's coming into our houses. And that's what's being filtered out when you're living in a passive house. And the last thing to say is you can open your windows whenever you want in a passive house. But the key is you don't have to open them to get fresh air because that's what your ventilation system's doing. Next, the one probably passive house we're most well known for is being really airtight. It's also the one that the contractors fear the most. Passive house has to be really airtight because when air leaks, it takes heat with it, and that's losing energy. So this graph here is showing that. This is a passive house building, and all that's changed between the graph on the left for energy use on the right is they've increased the air leakage. The one on 0.6 air changes per hour is what passive house would meet. If we bump that up to 10 air changes, we've got a third more energy loss, and that's just in little cracks leaking out of the building. So to do an airtight design, you need really careful design, and architects need to consider buildability, keeping it simple, because you need to make it as easy as possible when people come to site and are building the airtightness, and they have to get really good workmanship to do it. And last but not least, we have thermal bridge reduced design. So a thermal bridge is anywhere there's a gap or a reduction or a change in geometry to insulation. And the building everyone uses to explain what a thermal bridge is the Aqua Tower in Chicago, which is in the middle, and on the right is a thermal heat image. All of those balconies are not thermally broken, so they're just leaking heat straight out of the building. So when we look at thermal bridges for passive house, we're looking at two things. We're making sure we're limiting the amount of heat that gets lost through them, but we'll also have to check that we don't have lowered surface temperatures on the inside of the building that get so low that we would have a risk of mold or condensation. So we calculate something called an FRSI. It's a surface temperature factor, and we always have to stay above that number to ensure there is never any risk of low surface temperatures. Technically, the same thing exists in the building regulations, but it's not actively checked from what we can see. It kind of relies on a building inspector going, oh, can you look at that detail for me? whereas in Passivhaus, we actively check it for every interface. And one last just high-level design principle that really needs to be mentioned is the form factor of a building. This is going to have the biggest impact on how easy it is to achieve a Passivhaus or how much costly it's going to be. So this is a ratio of the surface area of the thermal envelope divided by the floor area. So what you want to do is minimize the external surface area where your heat is lost relative to your heated volume. So you're going to be penalized for things like complex geometry, cantilever elements. All of that is going to increase your external surface temperature, but not necessarily your volume. So on the left, the diagram shows the lower the number, the better. So the bigger the building gets, usually the better the form factor, just because of that ratio. And especially if you start getting into small buildings and you start doing quite complicated geometry, you start getting into really poor form factors. And these are 2-hour buildings, and it just shows you the difference. So this is a smaller building. You can see it's got a higher form factor. And look at the difference in the U values. We needed less insulation on the bigger building to get exactly the same performance. And that's just the form factor working for us. Now, I'm not saying you can't have complex forms in buildings, but we do need to understand that there's an energy penalty, and that's going to need to be compensated somewhere else. So I would argue as architects, we can be smarter about the ways that we articulate our buildings and not trying to do it with the insulation layer. Okay, so I'll now delve down kind of another layer, go into a few design details. The first thing to say, as a Passivhaus consultant, we're not the designers. There's always an architect, engineers on the job. The way we do it at Delta Q is we make sure we're embedded into the design team so we can work collaboratively together. We don't want to be a sustainability consultant that someone emails every 3 months and says, oh, can you check this U value for me? That's not going to work for Passivhaus. So we want to be involved from an early stage, supporting with feasibility, doing iteration modeling in PHPP. And then as we move into the detail design, we're reviewing all of the architectural details, working with the architects to suggest improvements. So very high level, when we're looking at reviewing buildings for Passivhaus, I like to break them down. So we're looking for the thermal envelope to be a continuous wrap around the building. We need a wind-tight layer on the outside of our insulation to protect it. And we need a continuous airtight line on the inside of our insulation. And then we need to find all of our thermal bridges and interrogate them and potentially mitigate them. So just a bit of a case study here of one of our projects. This is a social housing project for Newham Council. It's a 13-story concrete frame with steel infill, and it's 57 flats, and this is one of our typical floor plans. Now, because it's a pretty big building, we've already got quite a good form factor, but the architects made some other moves which were quite clever. So on the left is the architect's Revit model. On the right, this is our design pH thermal model. So this just follows the line of the insulation. And what you can see is they have done a number of inset stacked balconies. So those are sitting outside the thermal line. So when you see the actual line of the insulation, it is quite blocky. So this is what I mean by there are ways to articulate a building, and that can sit outside the thermal envelope. So we really want to reduce the insulation line going in and out, in and out, in and out as much as possible. What we also need to do quite early on is, very early, is just to find the extent of that thermal envelope. In a block of flats, there's always going to be some spaces that are unheated, cycle stores, bin stores, that type of thing. The key is anywhere we have a different thermal property like that, we have to have the walls separating it and the soffits are all going to have to be insulated and made airtight to Passivhaus levels. Then we'd be using the PHPP to define some U-value targets. Usually those are going to be a bit iterative as the building is being designed. And it seems pretty obvious, but yes, you're going to have to space-proof your insulation. The reason I am putting this one up is because when space gets tight, for some reason, architects always choose the insulation to start shrinking it down, and it's my job to argue with them. We can compromise on areas. The bigger your building, your form factor is going to allow you a bit more flexibility, but it needs to be done intentionally, and we need to do modeling to check it. So these areas always kind of come up as problem areas. Terraces over warm areas, you've probably got to drop the structural slab to be able to get enough insulation in there. All our nice recessed brick, we have to make sure we know where that is because it can be eating into the insulation zone. We need to take that into account in our U values. Roofs are always a challenge because as we get to the top of the building, there's always planning limits. And I always see the insulation on top of lift shafts and stair cores is always kind of squeezed down on less than the rest of the roof. And you need to understand all of the drainage early because all your tapering, all your gutters, we need to make sure that we haven't just got tiny bits of insulation in those areas. And if we've got any unheated spaces, then we're potentially going to have soffit insulation. And I always have cycle stores clashing with soffit insulation. It's always a challenge. So once we've designed our thermal envelope, we'll know the line of our airtight line because it's going to follow that. But we need to go now to a next level of detail. We need to know where that airtight line is going to sit within these build-ups. So when we're thinking about airtightness, we've got to think what materials in each build-up is going to be the air barrier. Now, some materials are inherently airtight, in situ concrete, screed, you can rely on those. Some will appear airtight, but they are not going to be airtight for the life of the building. Silicon sealants, for example, yes, they're airtight when you first put them on, but they degrade too much, so we would never rely on them as the primary airtightness line. And other materials are not remotely airtight at all, like blockwork, and they're going to leak like a sieve, so you're going to have to apply some kind of finish to them. So you're working with products like this, airtight boards, membranes, tapes, airtight paints. So what we end up having to do, I've just grabbed a bit of our building here, is you have to go through every single build-up, work out where exactly and what material is going to be the air barrier line, and draw a line as it goes around the building and make sure it's continuous, and you need to do this in plan and in section. And the key is there should only ever be one primary airtight line. So we do hear people go, oh, in this build-up, I've got two membranes, so I've got a backup membrane. You never want to design it like that because it gets too confusing, and if the builder thinks they've kind of got a backup line, potentially you might put a little less effort into your primary airtight line. So we always say there's one line within each build-up, and it has to be continuous. And once you've got that line, you then have to look around all of your interfaces and understand if you're going to have any special sequencing you need to consider. So this is just one example. I've got blockwork party walls hitting an external airtight line. If I zoom into that detail, on the left, this is how we'd like to do it. If the concrete frame ends up aligning with that blockwork wall, this is a really simple detail. We've got parge coat or airtight paint on our blockwork. As it meets the column, I put a bit of airtight tape on the junction, we're done. If, on the other hand, it didn't align, or maybe I don't have a concrete column there at all, now I've got to get into sequencing. Now, before they build that blockwork partition, I've got to make that line airtight. And potentially, I'm going to be bridging some insulation. I'm going to be putting airtight tape there. This gets a whole lot more complicated. So we always say with airtightness, try and keep it simple. Also talk about orientation and glazing. There's actually a misconception in Passive House that it means passive solar, that we're going to try and maximize the solar gains. We're going to have lots of free heating from that. So we're going to put all our habitable rooms to the south. We're going to have big windows there, and then we're going to have on the north, we're going to have small windows. Someone called this a passive solar fantasy the other day, which I quite liked. It's just too limiting in reality. Most sites, especially in a city, are not going to have the luxury of choosing their orientation like that. And for blocks of flats, again, our example floor over there, they have flats on every orientation. And if you have a certain view, I was reading about a passive house yesterday, it's on the north coast of Scotland. You're building a house on the coast, you're going to want to look towards the sea. Beautiful big north-facing windows in Scotland, and it's a certified passive house. So rather than talking about a preferred orientation, we definitely do look at orientation, but we use PHPP to run window balance calculations, and here on the right are some examples. So we are looking at the net gain and loss in winter versus summer, and we're trying to balance that out. So you definitely can't have highly glazed facades in passive house. So we would not expect to see floor-to-ceiling glass everywhere. And we work with the design team really to iterate glazing ratios dependent on the site, including overheating analysis. So if you see on our elevation there, you can see there's some opaque panels below the windows. We actually inherited this project at stage 3, and it did have full height glazing. So we had to kind of pare that back and have less glazing. The only place there is full height glazing is on the balcony doors, and those are strategically all placed in the balconies where they're shaded. So it was a way to kind of work that into the design. Space proofing of ventilation, if I have one plea to architects, it's care more about ductwork. For our mechanical ventilation system, it's so critical. For it to function efficiently as possible, it needs to be near the external wall, because we need to keep the intake and the exhaust ducts as short as possible, because the longer they get, it starts affecting the heat recovery efficiency. So if we start with a 95% efficient unit, and then our ducts start getting longer and longer and longer, we're starting to go 85%, 80%, and suddenly we're really impacting on the energy efficiency of our building. Now this is pretty hard to do actually, especially in a block of flats, because external walls are at a premium, and probably people don't want to be putting, you can see on the left, that's an example size of a MVHR unit. Probably as big or maybe a bit bigger than a typical gas boiler. So yeah, it is hard to do, and you have to space proof it from the start. You also need to leave enough space for your ductwork to go around. There's a brilliant example we were just looking at for MVHR, massive MVHRs being installed in the studios down there. Obviously we're in a retrofit project, so it's a bit harder. But ceiling voids, again, always squeezed down by architects. We need to care more. This is really important. Sorry, a little pop-up came up on this. And this is just an example for one of our projects. Again, it was one that we inherited. So already, this is the outside of the building on this side. Already the MVHR had been not placed near the external wall, okay, but we couldn't even take the ducts directly to the external wall because everything else on the elevation had been prioritized before the location of the MVHR grills. So you really need to be thinking about this pre-planning and prioritizing the importance of the MVHR, the grills and the ductwork. And when it comes to thermal bridges, with concrete and masonry construction, thermal bridging is going to be more challenging than, say, a timber frame building. We've got a lot of metal and concrete penetrating the installation zone. Usually the good thing is they tend to be bigger buildings, so our form factor is going to help us. So in Passive House, we will require more details from the architect because we need to understand every critical thermal bridge, and we need to clearly detail it to tell the contractor how to build it. So as Passive House consultants, we, as early as possible in the project, we start analyzing thermal bridges, and we want to do output. This is one of our project examples on the left. So this quantifies all the thermal bridge loss in the building. And seeing it like this allows you to understand where should you spend the time and the money mitigating thermal bridges. And this example is pretty typical for concrete frame. Usually the biggest thermal bridge we have is the masonry supports. These are the metal supports that hold up brickwork on the outside of the building, followed by the window and door interfaces. And we spend a lot of time looking at window and door details in Passive House to mitigate that. And on the right, this is just an example sketch of one of our projects where we're involved with the design team, looking at maybe thermal bridges that haven't been identified yet, suggesting improvements with the architects. And when you're looking to address the thermal bridge that you've found, there's basically two ways you can mitigate that. You can either break the heat path, which means you put a thermal break in there so something has a better thermal performance, or you can extend the heat path, like the example on the right. Now, the one on the left is going to perform better, but the one on the right is probably going to be more affordable. So we tend to use a combination of both, depending on that pie chart and how much is having an impact on the building. So just to look at one in detail, this is an example of, this is an internal wall. It's one of those walls on a thermal boundary. So it's got a heated space on one side, unheated on the other. We've got some nice insulation in our wall, but our slab just goes straight through. So now we've got a thermal bridge coming through the slab there. So you can see here on the thermal image, oh wait, I've got a clicker thing here. Let's point at something. Oh, there we go. So the light, you don't want light colors on the cold side because that is, we don't want this concrete to be warm because that means the heat is leaking out over to this side. So this is a particularly bad psi value, and that FRSI is starting to get quite low. As soon as it drops between 0.7, we'd be starting to get a bit nervous and worried about surface temperatures. And here's the 3 ways you can make it better. So the very best one is to put, as I said, a thermal break in the concrete. Can you see how now on this side, it's all dark blue? That heat is now kept on the warm side. We do have projects where there might be a structural reason why you can't do that. In the middle, it's kind of a halfway house. It's got some basically metal shear dowels, and we've just put a block of insulation in there. Still doing a pretty good job. And on the right, this is where there is still no break in the thermal slab, but we've tried to do something. We've extended the thermal, the heat path. So this is just a bit of PIR under the slab. It performs the worst out of all of these, but much, much better than our original detail. It was unmitigated, and we don't have any issues with surface temperatures anymore. So I thought I'd just show an example of if you just get a detail and you wanted to just assess it for thermal bridges, how you might approach this. This is an example that was sent to me recently. It's actually not a Passivhaus project because we wouldn't probably do details like this exactly. So this is a ground to party wall interface. So the first thing I would do is understand what are the boundary conditions. So I've got 2 heated flats above, and this is a suspended floor. So I've got a cold ventilated floor below. And I always suggest to architects, if you're struggling to see if you've got a thermal bridge or not, just color in the insulating elements. So here's my insulation, and all that block work is just standard block work. And hopefully it just jumps out at you right now. That insulation is not continuous. So I have 2 big thermal bridges where heat is going to leak down through this block work. I might even be concerned with that one. We might actually have surface temperature issues. But it's quite easily fixed. If we swap out some of those blocks for thermal blocks that have a much better thermal conductivity, now I have a continuous thermal line through here. I've still got a thermal bridge, and I still have to calculate it, but I've mitigated and it's going to perform much better. And I was just going to say a few last words about what happens when we get on site. As Passivhaus consultants, we follow the project all the way through construction. We work with the contractor, spend a lot of time on site doing toolbox talks and training. We do site inspections for quality and benchmarking. And we're helping the contractor gather all that evidence that they're using the correct products and that they can demonstrate that the workmanship is good enough for Passivhaus. So here's just a few examples from work we've been doing. So we spend a lot of time talking about how they're going to install stuff, hopefully before they do it. So how are they going to install the insulation, store the insulation so it doesn't get damaged? How are they going to cut it so they can get nice crisp cuts? How are they going to install it? What sequencing? The bad example in the middle happens all the time. I see some very nice insulation going in. This is a door threshold, and you're looking down on some insulation. So someone does some nice work and then it doesn't get protected and then it gets trashed. So we spend a lot of time encouraging contractors to do protect works, protect insulation from getting wet, all this kind of good stuff. And we spend a lot of time also on air tightness. This is where sequencing is really important. The example on the far left, this is some timber joists going in, and the block work had to be made airtight in that area before then. So you can just see the purple airtight paint, which is just a strip's been painted there, just so that they can get those joists in. And in the middle, we've got wrap-tight, which is an airtight membrane, and then the silver, which is zoomed in on here, this is the EPDM around the window, which is making up part of our airtight line. Now, can you just see the EPDM is just starting to lift? Again, I need to point with this. Here we go. It's just starting to lift away here. Not very much. That's enough for air to leak out of it. And when we do air tests, we use non-toxic smoke, and you'll stand here and you'll see smoke leaking out of this. So it needs to be absolutely 100% air sealed for Passivhaus. This is another side example. So they were installing the ground beam. So in this detail, it's this block of concrete down here. And you can see later on we had to come and install a piece of rigid insulation wrapped along the side. So we first turned up on site and they'd just used some Corex, some floppy plastic as the shuttering. which we immediately pointed out, how are you going to come and put a piece of rigid insulation against that and not have a big gap behind it? So fair play, the next day they had some proper shuttering out there and getting a nice crisp line. That's what I mean about we really talk about how they build things so that we can get the best quality. And this is the last example up on a roof. This one over here, when contractors are installing a big roof, they'll insulate it over a couple of days. So they'll maybe put some insulation down, and that evening they'll immediately waterproof it and wrap the waterproof down onto the slab. And that's to protect the insulation, which is great, but it's called a day joint. The next day they come back and they just keep going with the insulation. And if you do that, you get this big gap. It was big enough I could put my hand into it. We've just created a thermal bridge on our roof. So we have to ask contractors, when you come back the next day, you need to cut the J-joint back out so you can butt the insulation up with no gaps. So we're starting to kind of talk to contractors about interrupting things they do as standard, which they need to do differently. And in the middle, this is an example of rejected work where they're using damaged boards. They're not doing a very good job of cutting. That's creating gaps. None of this is acceptable. And I think I'm always at the end. So yeah, in conclusion, Passive House is really about considering the energy implications of every design decision. Keeping it simple is definitely the trick, and you need to think about it from the very start. The number of times we get someone who's already gone through planning who goes, oh, I want to make this into a passive house. It's not too late, but it's going to be incredibly hard and costly to do it at that point. So if you are interested in Passive House and want to learn more about it, it's really great. There's some free training that's offered for all REBA accredited architecture students. You can find it at Coaction. It was developed with REBA. So it's a free online self-study series of modules. There's also Coaction who Delta Q train with. They also offered, if you wanted to do the full Certified Passivhaus Designer course. And I've got some further reading here. I can kind of send this out for Will if you want the links. And that's the end, if anyone has any questions. Thank you. Hi, yes.
Does the certification expire on a passive house? For instance, if seals break on windows and triple glazing, on triple glazing, if the seals break, you have to replace the window. Mm-hmm. If the air tightness tape fails, then the U value will increase. Does the certification expire at some point for that reason? Or?
It doesn't. So passive house certification only occurs once you've first built it and then you certify. But there have been a series of tests to look at the longevity of passive house. So they've tested that very first building I showed, which was the first one that was built, and a series of other ones. And what they found is you'll always have to replace windows last 25, 30 years. At some point, they will always need replacing. There's a study that shows that they did air tightness tests on a passive house 20 years later, and it was still less than 0.6 before they replaced the windows, and then it got even better when they replaced the windows. And that's actually that's one of the things with the quality and the air tightness products. We will only choose products which will last the life of the building, or a window that we know there is a maintenance cycle that when it fails, it will be replaced. Yeah.
Is it possible to, because my parents have this problem now where the double glazed seals are broken on the windows, it's on a passive house, and they have to replace the entire window and get a new one, as opposed to it being shipped off with the seals replaced and then delivered back to the site with a much lower embodied carbon than replacing the entire window. Okay, is it possible to have seals replaced as opposed to get a new window completely?
Yeah, you could. I mean, there's nothing special other than the fact it's triple glazing. It's just a window, so you can treat it like that if you'd like to, yeah. And if there's nothing else wrong with the window, you just needed to upgrade the seals, then that would be a great way of doing it, yeah.
I was wondering if the new 2022 London's push for dual aspect residential building affects passive house planning very much, considering the building forms is not very simple anymore, and it tends to be a little bit more funky, especially if the building's quite big.
Mm-hmm. So it was the dual aspect?
Yeah, that push for like an almost 100% dual aspect residential blocks, buildings.
No, I don't think that would, because I don't think that's going to necessarily affect the form as much as you would think. I haven't really seen dual aspect be a problem as much. What is interesting is the new fire regulations in blocks of flats that will require 2 stairs. That is actually going to have an effect on the treated floor area calculation in Passive House. That's one, rightfully so, it should go in, but that could actually have an impact on Passive House buildings. But no, I haven't specifically seen any issues with the dual aspect. Yeah.
Okay, thank you.
Hi Megan, thank you very much for the talk. It's a question, I'm not sure if it's a strange question, but with the principles, would Passive House work in places like where it's really extremely hot, like Asia? You know, places like Thailand or something like that. Does Passive House exist over there?
Yes, it absolutely works in the reverse climate. It works the same as if you think of in the UK, we're dominantly heating in our buildings, so we're trying to keep the heat in and the cold out. You just reverse that in a hot climate, so you keep the cold in and you keep the heat out. So you still want it to be super insulated and airtight, and you want a ventilation system, but there you're trying to keep your main limit is your cooling demand is going to be the hard target that you're trying to meet. You know, you're not going to have a heating demand issue. There are some countries, I can't remember, someone was reading it the other day, where they have a sweet spot where they don't really need heating or cooling active systems, that if you build a passive house, because they have such a climate that's quite average, you can make it work without either of those. But yeah, it's all over the world, yeah. And
like, for example, if you were asked to do projects in the Philippines, so you'd have to go out there and then, you know, check it, and then you'd have to be a part of the whole construction process as well, because you'd have to make sure that they would be building it according to the details. I think this is where a lot of things happen on site, where even though with the best intentions you give a detail to build, you know, the construction team will just do what they want, or they won't do it really well. So in a place like Asia, where sort of the quality of building is, you know, a bit thin sometimes, and I've seen it myself, what would be your role as passive house consultant? Would you have to keep on going out there to check, or would you just have to, you know, do another way, do videos? Like, how would it work?
Well, I'd hope you could find a local passive house consultant, because you definitely wouldn't be flying out there all the time. I know certifiers, which is the independent certifier, they don't necessarily have to see a project. So we have the Passive House Institute in Germany certifying some of our projects, for example. So they do everything via photos and videos. In theory, I mean, we have done it ourselves when maybe we can't get to a site as easily, and we'll do a video call. Would it work to get that absolute performance gap down to be decided? I think you need a local person on the ground who's going to be your checker. I think you need to be going to site to see stuff. I think if you tried to do it all remote, the number of times I go to site and it's just like, oh, what's happening over here? You know, it's just the periphery stuff. And just being there all the time as a passive house consultant, people getting to know you're going to be turning up a lot, you're going to be querying, everything they do is going to be checked. The contractor gets in this mindset. And the great thing is that almost everyone I've worked with and subcontractors are really up for learning about this, and they're really up for getting the quality. If they buy into the idea, you're halfway there because you've got the mentality. I do think you need someone on the ground, yeah.
Thank you.
Hi, thank you so much. Sorry to keep you all here still. I have one question in regards to embodied energy and passive house. Obviously, for new build, passive house makes complete sense. My question would be, what's your view in regards to retrofit, and how, I suppose, the cost of retrofit and the difficulty of doing passive house in an existing building, how that weighs with maybe, you know, operational energy comparison, you know, to improve that. How would you weigh passive house for retrofit, and do you think passive house standard makes always sense, or are there caveats where you think actually air source heat pump and some, you know, if you look at cost versus result?
Yeah. No, I think it's a completely different animal when you're into retrofit. So there is an NFIT standard for Passive House, which is a bit more relaxed, but it's still incredibly hard to meet. And actually, there's a lot of work being done in this space about what's the sweet spot for retrofit. And actually, I think a lot of the time the argument is you might not go all the way to an NFIT, especially when a lot of the retrofits that are going to take place are going to be step-by-step retrofits. Most people are not going to have the money or the time to suddenly rip out every part of that building and be able to do a whole NFIT to it. But what you can do is you can still use all the Passive House principles still, even if you're doing, you know, PHPP is a much more accurate way of modeling energy use, including in an existing building. I would never rely on a SAP model, and EPCs are not worth the paper they were written on. I would want a PHPP model, and that would tell me exactly where the energy is going, and in a retrofit, where should I start, you know? If I do an analysis of thermal bridges in an existing building, I can understand, do I have any surface temperatures I immediately need to deal with? Where should I focus my time and my money? The same principles can apply to a retrofit, even if you're not going to go all the way and try and meet those safe criteria.
Thank you. What in regards to embodied energy?
Oh, yeah. Did you see the embodied part of my talk?
Sorry.
No. Well, I'll just repeat the one main part of that. I was going to say, otherwise I didn't explain it very well. I'll just say repeat the bit that basically you can, Passive House can be made out of any materials. So we see it as compatible with embodied carbon strategies. It doesn't work against them in any way. Yeah.
Thank you. I guess my question's about ease of replacement of the filtrations in the ventilation, because I feel like to me that would be the one part where you said every 6 months you'd have to replace it. To me that's the one part where it's like the handed off thing, where it's the either if it's in like a block of flats or if it's a person's house, that's the part where it fails. Like the Passive House it's like you're no longer in charge of making it passive. It's the client, it's the person that's living there now that's in charge of like doing that. Is there a way to make that just so much easier in terms of, hey, there's like a timer limit, you know, when it's 6 months, then like you gotta, it's like a beep beep,
yeah,
replace it, you know?
Thank you for bringing up that, because that is absolutely something we work on. First thing is, I didn't mention it, but you absolutely have to make it the MVHR accessible so you can change the filter. I was looking at my sister's flat, it's 10 years old, and actually has an MVHR in it. And we found it, and it's in the ceiling, and she has to get up into an access hatch. And then I read the user manual online, and it said, take out the ducts from the MVHR, take out the heat exchanger, and then clean it. I was like, yeah, that's never going to happen. And it said, do it every 6 months. No. MVHRs now are very user-friendly, so you've got to make sure you can get into a cupboard easily and replace it. But at the same time, I agree with you, because we're having lots of conversations about, this is a different way of living. It's the same way people need to get their heads around living with a heat pump. I mean, are we there with knowing how to repressurize a gas boiler? I think we're kind of there knowing how to live with that technology, and we're going to completely switch to living with MVHRs and heat pumps. And if you don't change that filter enough, it will get blocked. It will start affecting the efficiency of your MVHR. It starts to unbalance it. So we always have user guides. We've got to educate people. But we're also having conversations about, say, in social housing blocks, who should be responsible for those filters. And actually, we had an interesting conversation the other day where a housing provider was looking. Could they locate the MVHR so it's kind of near an external wall, but so that there was a cupboard from a communal corridor that they could access, so they could swap the filters without having to get into the flat? And I was like, that's interesting. So really trying to think through what could make it fail in the future, and how do we work around that. But it's definitely a good area to think about.
Well, thank you.
Well, thank you, Megan. I've just got one other quick question, but a great talk, and so useful, and it'd be nice to have that slide.
Yeah, sure.
Do you know of any passive house projects where they've used vacuum insulation?
Oh, we don't recommend those. Boo. The Passive House Institute, I think, won't even accept the use of them, and they're very prone to kind of failure and not having confidence in their thermal performance. So probably not, no.
Okay. I mean, it's quite interesting technology, but yeah, I can see it going wrong. One of the things in installation is you have to do a lot of work with manufacturers to get the proper tests to prove that the thermal conductivity is what they say it is. And the Passive House Institute does a lot of research into that. So it's not saying at some point they might have confidence in it and the manufacturing will get better. At the moment, we're going through a lot of, do you know what PIR insulation is? They're actually downgrading PIR because they've done research now that when you put it on roofs, it tends to shrink, and then you get a reduction in the thermal performance over time. So now whenever we use PIR on a passive house project, I have to put like a markdown on the thermal conductivity to allow for that shrinkage over time. So actually we're trying to talk people out of using PIR and to move to other insulation. So it's all about what can you evidence and what can you justify over the lifetime of a building. Thanks so much. That was great. Thank you.
Thanks for having me.